Hey sports fans, welcome back to Wendy's Mismatchups of the Week. Here's a look at the showdowns that are as lopsided as the rivals.
Okay, I've got some sound here, and of course I've been giving a nice little intro to the ESPN College Football Playoffs theme and screen. This is, of course, if you can hear me, the first week where they'll be doing those college football rankings. Some exciting stuff. Now, here's what we've got going on. Okay, this is Module 11, or Week 11, if you will. And we're going to take a look at Hammond's Port 1, which was due last week. And we're also going to talk about Hammond's Port 2 that is due on the 10th. Chapter 12, you have an exam that's due on the 10th as well. And the 10th obviously is Friday. And I've got some resources here about waiting line models, Poisson distribution, using the norm inverse function, and we're going to be using it in Hammond's Port 2. So we've got some good resources here, and I am starting a little bit early. In fact, started a little bit earlier before, as I was using that wonderful ESPN College Playoffs music and screen from our friends at YouTube. Well, I'm going to go ahead and get rolling here, and the first thing we want to talk about was the Hammond's Port 1 case. And here again, you know, we're working on waiting time, and I'm going to download this, okay, and the key. And we'll open that jewel up. Here we are. And what I'd ask you to do, I'll move this over here, okay, this is the key. I'd ask you to use goal seek to obtain a probability of waiting to 0.55 by changing the largest value for interval times, okay? And let's talk about that for just a moment. We have the enter arrival times, okay? And again, if you take a look over at page 569, you're going to see the two enter arrival using a 2 ATM system. Okay, so we've moved from Hammond's Port 1, which used 1 ATM, and now next And now the assignment that's due on Friday will be Hammond's Port 2, where we have 2 arrival times, or we have 2 ATMs, okay? And so we're trying to look at the smallest value, which obviously would be 0, and enter arrival time means, you know, as people come. Now, if you look at the top of page 569, table 1211, you're going to see the simulation results. Customer 1, who arrives at arrival time at 1.7, okay, and they start their service time. They have no waiting time. They have a service time of 2.1, so they're out of there in 3.8 seconds, minutes, or whatever, okay? And the time of the system was the 2.1, okay? And then the time for ATM 1 and ATM 2. So we don't have those figured in yet. And then you see the enter arrival time just starts to build on that, okay? And that's where we get the enter arrival 0.07, 2.4, and that just simply, and we're using 1 ATM, but you see it goes from 3.8, the time available at ATM 1, down to it goes down to 5.8 as we move down to customer 3, and you see it build progressively, okay? So that's what's going on there. And here we have these customers. Now, remember, this simulation, this is a simulation involving 1,000 arrival times, okay? And they use the freeze to cut it off to give us the first 5 and the last 5 of those 1,000. So that's what you're seeing. So don't let that confuse you. If you get confused about that, take a look at row 20, then you'll see row 10, 11, okay? That's what they're trying to do. Now, the largest value, okay, was 5.2, okay? And that's how we end up with a probability of waiting time to change to 0.55, okay, by getting basically that largest value for enter arrival times. And so we use the goal seek to obtain a maximum waiting time, and we end up time to 9.5 by changing the mean service time. We just use the goal seek and apply it to those variables, and that's all. And that's really all that we're asked to do. So that was pretty much, should have been a fairly simple exercise to do. And here we got the probability of arrival time, waiting time, to 0.54. Okay, as you see, and we use the largest value up here, and then we use goal seek to obtain the maximum waiting time to 9.5. Okay. By changing the mean service time. So we could do that, and we'll go over here, we'll look at data. Okay, we'll click on data, we'll go to the what if analysis, we'll go to goal seek, and we want to obtain the maximum, we want to get a maximum waiting time value of 9.5. Okay, so we want to get the maximum waiting time value, and we want that to be 9.5. Okay, by changing the mean service time. We'll click over here. Okay, and then we'll run the goal seek, and it's going to work through some iterations. You can see as it's running the simulation there. Okay, and we end up with the value. Hi, glad to see you. Now, I started a little bit early, and let's see who this is. Welcome, Jan. Glad to have you here. And you'll want to double back. I started at about maybe 10 minutes or 12 minutes early. You'll also don't miss. I've got it in the screencast. The ESPN college football theme, because this is the first week. The playoffs, they're doing the seeding for the top 4. So in that honor and that exciting time period of American sports, I've got that on there. Nonetheless, we went back over also what we're doing this week. This is module 11. And I'm going over the key for Hammond's Port 1, okay? Now, the first task was to use goal seek to obtain a probability of waiting to 0.55 by changing the largest value for enter arrival time. So, and then the second was to use goal seek to obtain a maximum waiting time of 9.5 by changing the mean service time, okay? So we ended up with a mean service time, okay, of 14.7, okay, and our target value was 9.5, okay? And so we changed the mean service time. That's the best that we could do with that solution. And again, we ran a simulation, okay? And we could keep doing this, but we've got 1,000 simulated cases, all right? And again, I got the maximum waiting time of the maximum waiting time there, okay? And ended up with 14.7, and the target value was 9.5. So we ran the simulation to see if we could indeed get that done. And it was just simply a matter of this case was just simply a matter of putting those values in, okay? And let's just, we'll do it one more time. And we're going to, first of all, we're going to use goal seek to obtain, this is the first question or first problem, probability of waiting time to, and we'll go into the goal seek. And we want to change the probability of waiting to 0.55. And we'll go right here. And that would be 0.55 by changing the enter arrival times, okay? And we'll go up here. And the largest value for enter arrival time, okay? And we'll click here. And we'll run it. Now, you're going to notice if you look here in the simulation itself, all right, we come up with the value, target value, largest value is 5.1. This is up in terms of enter arrival times, and then the target value of 0.55. We achieved that. Now, a couple of things I reminded everybody, and you don't want to miss this, is on the simulation. This is, we are using 1,000 cases. They just simply froze the screen, froze this right here at the first 5. So you'd see them, and then we hid basically everything between customer 5 and customer 996. So we could see the first 5 and the last 5. If you wanted to unhide all that, you could, but it doesn't really matter because the output we're after is over here. And so we got the goal seek, and we got a target value of 0.55, and we achieved that by changing the largest value for enter arrival times. Okay, and that's 5.149. Okay, and when you think about it for a moment, okay, we're upping that mean time, so we're going to be increasing the enter arrival times. Now, as I mentioned earlier, if you look over at page 569 in the book, table 1211, you'll see what enter arrival time is. Okay. And how, as you follow across from that customer, the time and system grows with each iteration, okay? And they show you 10 of them there, and you can just see how that enter arrival time. And so we're talking about people, one person comes in, and then they're being serviced, then another person comes in, they're being serviced, etc. This is for one ATM. This is Hammond's Port 1. Hammond's Port 2, we'll look at a situation in which we have 2 ATMs that we're working with. Now, we're gonna do this. We're gonna use the goal seek to obtain a maximum waiting time of 9.5, okay, by changing the mean service time. So we're gonna click OK on that, and then we'll go back to what if analysis. We'll click the goal seek, okay, and we're gonna use goal seek to obtain a maximum waiting time of 9.5, okay. So let's go over here to the maximum waiting time, and we're going to make that 9.5. Now, again, these figures that we're using for these goals might be industry standards, these might be budget issues. It could be any one of a variety of reasons why we do this, and we'll change the mean service time. And we'll find this over here, the mean. And so we're going to set cell E 1021, okay, and E 1021 is the maximum waiting time. Right now it's 7.6. We want it to be 9.5, okay, by changing the cell, by changing the mean service time, which is over here at B8. Click OK. Let's see what we get. We're going to see it run through the simulation. Okay. And we'll see what we arrive at. And to get the target value of 9.5, okay, we're not able to do that. We end up at a current value of 14.8. So we see a limit there in terms of the simulation and what we can do. So that's Hammond's port number 1, okay? That's really all you had to do. Now I'm going to cancel this off and I'm going to close Hammond's port number 1. I've got it there for everybody. I published it this morning. Let's go back over to the module, okay? And we looked at Hammond's port 1, which was due last week. And I want to show you a screenshot from there as well of that for you. It shows you, and we can zoom in on it a little bit. Now remember, when we do a simulation, it's important to understand something, okay? We are dealing, when we run a simulation, we're creating values that are volatile, okay? And now you can go into Excel and you can change the settings so that you have non-volatile data, but you really don't get the same kind of result that you get if you just do the simulation. And the simulation is intended for me to use a mathematical model of the probability distributions. And there's a link to a video where I talk about that, okay? Now, Hammond's port 2 is due on the 10th, and Hammond's port 2, okay, deals with 2 ATMs, okay? And you're going to find that over on page 570, they talk about the Hammond's port 2. Let's just go over here to the files, okay? And we'll find those. Put this up. And we want to go in and find the, not the Foreman files, that was from the Data Smart text. I want the MIS web files, here they are. Or the MS13 web files, excuse me. We'll download them. And we're working with data from chapter 12. Okay, and we'll click on the Excel files, and there's Hammond's port 2. Okay, and I have some instructions for you on what you want to do. Here's the deal. In this situation, we have 2 ATMs. Now, if you go back over on page 569, okay, you're going to see that they have an example that shows you 2 ATMs. And that was when I talked about the enter-arrival time, okay? Then we start talking about 2 ATMs. It gets a little bit more complicated. Now, this is the authors begin a dialogue about this over on page 568, okay? And they walk us through starting at customer 6, each step, how those values arrived at customer 7, customer 8, okay? And then over on page 570, they end it with, so they show you customers 6, 7, 8. And so how that whole process is a series of iterations, okay? Now you got to, now, just so that our memories are refreshed, okay, we've got to go back and look at, first of all, over on page 563, figure 1213 that shows you the ATM simulation model. And we see that model there in a flow chart or data flow chart where they have the number of ATMs, which is a controllable factor, okay, and then the enter-arrival times and the service times, and those are probability laden, okay, and then or probabilistic, and then the output, that's the operating characteristic. All right, and we talk about the fact that we have a normal distribution, probability distribution. Then if you want to see the model in its full glory, okay, At the top on page 564, they show you the values. This is the mathematical model. Then they show you the full simulation model, okay, in a flow chart format with the decision points, okay, and then the outputs and all of the arrival times. And then those are just pulled over into the formula, over into the spreadsheet and worked on. Now, we'll look at this, okay? And let's look at this for just a moment to refresh our memory. And I clicked on cell B16, and let's look at it for just a moment. B16, that value, okay, is B4, okay, and that's the smallest inter-arrival time value, okay. And inter-arrival time, think of it, inter-arrival. So as people are arriving, that's what we're talking about, okay? How long are they waiting? We don't just isolate. The simulation is intended to deal with a flow, okay, not a truncated kind of situation. All right. Now, and that's added to a random value, and that's the random function that you see there, plus B5, which is the largest value for the inter-arrival time, minus B4, the difference between them. Okay, so you can see how we're coming at that. We're getting the smallest value plus that random number times, okay, B5 minus B4. Now, what we're really doing here, in all intents and purposes, is we're washing those numbers using the random function. That's all that we're doing. Okay. Now, let's move on a little bit here. Okay. And again, I have a task for you to do. Okay. And we'll go back over here for just a sec. Okay. And we'll go down to Hammond's port 2. And let's click on that. And here's what I'm going to ask you to do. Use GoalSeek to obtain the number weighting to 70 by changing the standard deviation for service times. Okay? That random number the random number we multiply times the difference between the largest and the smallest gives us a sort of standard deviation, because it mimics that, if for all intents and purposes. Now, Hammond's port 2 is on page 570, and you should really review pages 561 to 72 as background, okay? So you'll want to do that. Now, that's due on the 10th, which is Friday, okay? So that's the assignment that you have. So you're just doing some more manipulating of those variables. That's the whole point. What we're simulating, okay, is the summary data. We're not simulating. It's the raw data that we are. The raw data is here in the simulation. Okay, you notice as I was in there, okay, they're volatile. The numbers are jumpy. That's because they're simulated and they're designed to do that. Okay, and again, we've got that. We're just manipulating these inter-arrival times and service times. There are the summary statistics that we get. Okay, and we could try, and we'll experiment a little bit here for just a minute. We'll click on GoalSeek. We'll click on data, and I'm going to do what if analysis, and I'm going to do GoalSeek, and I'm going to set the probability of weighting. Okay, right now it's 0.1022. I'm going to set that at 0. Let's say I want to do a 10% improvement, so I'm going to do 0.93, I guess, by changing cell, the mean service time, So if I change the main service, I'm going to go there and do the main service. Boom. Okay. That'd be B. Okay. There we go. Now let's just see what happens. Now the value of this is we can run as many iterations as we want to. Now we had a target value of 0.93. Okay. And we had the current value, okay, and there we are in term, and we could see on the mean service time we're at 4.94, okay, but our average waiting time, we had a target value, okay, and not too good. So you can see that, and it's just all that we're doing is just manipulating those a little bit, okay. That is all in the world we're doing. All right, now I have some resources I want to share with you, okay, and we'll talk about those. Of course, you have chapter 12 exam due on Friday. I'll talk for a moment about Little's Law. I mentioned it last week, but we had not really talked some about it. And this is an algorithm or a law used to minimize waste and increase speed. This is from a website that deals with quality control. Okay, deals with what they call Six Sigma solutions, the best solutions to reduce these. And they show you Little's Law right here. Okay, which is the lead time equals the units, work in process units. Okay, and we have the ACR units. The ACR unit, the average completion rate, times the units per time period. And notice it's a ratio, okay? And so we can apply this and see, and they give us a nice example here of seeing how efficient and I think they use a service situation. They've got some related articles, but I think it's worth your time and trouble to go over and take a look, okay? Now, this is an interesting article, okay, that I really would encourage you to take a look at. This is one of those dramatic examples of how management science can really be impactful. And basically, this article talks about how Southwest Airlines, by shaving 10 minutes off the time it takes to service their airplanes, the thing comes in, it lands, it taxis up to the terminal, and then they've got to clean it, all that business, and restock it with the food, whatever they might serve, and all that business, refuel the plane. How shaving 10 minutes off of that process really up into the industry, okay? And the people at Southwest Airlines understood two things. One, the faster you can turn around, the smallest amount of time you have a plane on the ground, the inverse is the largest amount of time you have a plane in the air. And having a plane in the air is the moneymaker, okay? And this is important for Southwest for a very simple reason. They don't use a hub and spoke type of operation. They fly point A to point B, and their goal when they first started was to make sure that your flight between point A and point B would cost you in as much in fuel in gasoline that the price would be equal to or less than what it would cost you to just drive there. So they were saying, okay, we're going to make this an economical situation and a convenience situation by flying point A to point B, no layovers, okay? Then the next thing was, and if you've flown with Southwest, the times still do it, the flight attendants, they'll sing, they'll tell jokes, this or that, they'll talk about where you're headed. All of this because they understood that flying is more than just taking people in a tube and throwing them in the atmosphere. It's an experience, okay? And this is an excellent article that talks about a management science technique, and that is that shortening that time to service each plane. And think about it. If let's say you have, let's say you have 100,000 flights a year, and you shave an average of 10 minutes off of those flights, you've saved 10 million minutes, okay? And I'm just gonna, because I don't do the math real quickly, I'm just gonna ask the question, how many minutes in a year? How many minutes a year? And there are, 1 year is equal to 525,600 minutes. So if I shave 10 million minutes, pardon me, if I shave 1 million minutes, okay, I've basically been flying 2 more years than my competitors, okay? That lets me do some other things that really are, that really build my case for being an industry leader. So I think it'd be worth your while to take a look at that, because these management science techniques, as I've spoken about them, these are not just stuff to put in a textbook and torture you with. These are real life solutions that can be applied in the real world that have all kinds of applications. That's why in the first chapter, okay, we talk about problem solving versus decision making. And why in the first 2 chapters we talk about building a model, okay? And by doing that, we can simulate, as we've been doing, the real world in one way or the other, and then we can change how we interact with that real world. For example, in what we're looking at today with Hammond's port, they have 1 ATM, they have 2 ATMs, they have 3 ATMs, they have 4. And we talked about that before again, okay? The total cost of waiting time is a function of a couple of things. One is the service time, okay, and the waiting time. So I'll pop back all the way over back to the start of the chapter, okay? And they talk about doing that. I want to find that waiting line, and it's how much time the total time is the time I spend waiting and the time I spend being serviced. Okay? Now, if I increase service time, I can increase waiting time. And I have to determine, is it worth the total cost? It's a lot like inventory. But in this case, the inventory is not stuff, it's time. Okay? So I really do encourage you to take a look at that resource. I really do want you to do that. Now, got a few other things I'd like you to take a look at. We'll pop back over there for a minute. Okay, and there's also, here is another one of those, and I try to provide you some real world examples. This is from Six Sigma again, where they talk about reducing the work in process at a frozen food manufacturer. The more work you have in process, okay, the more you have in process, okay, the greater your cost, because you've got more stuff you're working on. And the whole idea today is this notion of what we call lean manufacturing, reducing the work in process so that we make just what we need, not too much, not too little. And they walk you through that at the process of how they have used these techniques to get that down and to get a true shift in productivity. And it's a case study, and they show you, they utilize a Pareto chart, which is really nothing more than a cumulative frequency graph reversed. And they show us the total percent of total WIP, okay? And they're talking about running regulated work in process. Either levels create a need for additional labor, excess transportation, etc. If you have too much stuff on hand, you got to put it somewhere. People have to handle it. It gets in the way. This whole thing, modern manufacturing, is really a science, and every square foot, every inch is utilized to the maximum degree. And you want to have the lowest amount of WIP WIP going through there for a simple reason. It just costs you more money. and it eventually adds to the price of the goods that you're trying to sell. So they show you some time series plots that walk you through the measures that they took, okay, and some of the solutions they employed, okay, and they even show you a nice flow analysis of the process. This is a good case study, an excellent one, okay. So I would really recommend that you take a look at it as well. Now, for just a second, okay. I think, again, I try to show you, try to provide you some resources so you could see. Here's another with Starbucks. Starbucks is very has to be very sensitive to waiting time, because everything is almost so tailor-made. You go and you order coffee, and they want people. If you've ever been in a line at Starbucks, you know what I'm talking about. Person wants this latte with blah 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 blah, and 6 different ingredients, this that, and you're sitting there going, I just want my coffee too. So Starbucks, in order to do mass customization, okay, we've talked about that, mass customization of coffee, which is what they've done, is they have to be very sensitive to waiting time and to lean operations. Okay? So they're very tightly managed, and they walk you through all of that, okay, and the process, and they show you the command line, and they walk you. This is a nice little infographic or schematic, okay, that walks you through that process. And notice, again, they talk about the distinction between service and manufacturing, okay? Now, when we talk about mass customization, what we're talking about is manufacturing unique service and product bundles for each and every customer or customer segment. So if you're a marketing person, for example, you're sensitive to this. So again, another one of those real world examples that I think are certainly worth your time and trouble to take a look at. Now, we'll go back over here, and I think it'd be to your advantage to take a look at. Now, here's a resource that covers basic waiting line models, okay? And they talk about the characteristics of a queuing system, queue discipline. What do we mean by that? If you say, okay, Dr. Harmon, the textbook's great, I want to see some real world stuff. Here it is. And you can see the applications. I think the most dramatic of all of these is Southwest Airlines, how they literally changed the industry and shaved time off waiting time. You know, the less time the plane's sitting there, the greater amount of time the plane's in the air, okay? And you make money by getting people from point A to point B, not by sitting on a tarmac. Now, let me back up for just a minute. And you know, we talked about 525,000 minutes in a year. It's 525,600 minutes in a year. And it's okay, theoretically, I saved 10 minutes, an average of 10 minutes on a million flights. On 100,000 flights, I've saved 1 million minutes. In some ways, that's bankable. You say, what do you mean? Customers will tolerate certain amounts of waiting time, and I've got a resource for you in last week. And how much does waiting time matter to people? People have pretty well-known thresholds in terms of how long they will wait. So, you know, when you can shave time, okay, off of service times on an airplane, and let's say this is the winter time, all right, and it's in winter, and you have a whole series of flights that are eastbound. Okay, let's take your eastbound flights. What are they flying into? They're leaving Las Vegas. They're leaving. They're going to leave over in. I think Southwest has a terminal over in Oakland. I can't remember where their terminals are in Los Angeles. Maybe even LAX, but I think there's a smaller airport. Phoenix is definitely has a lot of flights. Denver. Denver's problematic because you're up in the Rocky Mountains, you're up high, and they get a lot of bad weather. So when you start talking about, and probably from Denver on, you start talking about going west, from the west to the east, you start talking about flying into bad weather. And so they have to plan for that, and hopefully they build enough goodwill with the customer so that the additional waiting time doesn't kill them. Now, most of us who've flown in the winter know that we're going to hit bad weather, okay? And you account for it, and you'll see the things in the news, or the New York, all the flights in New York are canceled, and people are late. People who fly get used to it, and the airlines try to do their best to take care of people when those kinds of things happen. Now you say, well, what about east to west? Well, even though it's, you could be out here in Oklahoma City, it's a sunny day in December, it's maybe 45 or 50. Back east, everything's all stacked up. The terminal in Oklahoma City, Will Rogers World Airport, is sitting empty because everybody's back east. So these service times are important, and so understanding this and understanding the tactics we can use, okay, to lower time in system, okay, is the best way. Now, there are some situations where we want to increase time in system, or we want to increase the sense of time in system. Let me give you one that's a tried and true method. When you go to the doctor next time, unless you go for emergency, even if you go for emergency care, unless you're in critical condition, you go to the emergency room, you'll sit there for for about 20 minutes. Then they'll take you and put you in a room. You go to your doctor for your annual physical. The doctor will put you in a room. The nurse will walk you back there. What's the point? Well, then you feel like you're at the doctor's office, okay? And so you may or may not really notice that when the doctor comes in, most doctors today, if they spend 5 minutes with you, it's a miracle, because they're driven by the numbers of patients that they serve, especially in these larger system kinds of hospitals. Okay, well, I'm going to go back to, we'll go back over here, okay? I'm going to go back over. And these, again, are some resources I've got for you. Okay, now, we started, I don't know, about 10 minutes or so early, all right? And so we're about 11:35. So we've been going at this about 45 minutes. So I've got just a few more minutes, and I'll talk with you about that. Because I've got some logistical kinds of things coming up that I want you to be aware of. Basic waiting line models, and we'll make sure that you look at that. The Poisson distribution, we'll talk about that Wednesday, okay? Then we're going to talk about Excel's normal distribution functions, okay? And the norm inverse, what do they mean? What are they all about? Okay? And it's more about understanding a thought process than it is doing computations or using software, okay? You say, what do you mean? Okay. All of this is about saying to myself, if I'm dealing with a particular industry, okay, and I have a set of customers, what is the arrival time? What's the distribution like? If I know that it's more of a normalized type of distribution, okay, it looks like a Gaussian curve or a bell curve, that gives me one set of parameters to think about, because I can attach probabilities to that. And I know that, between 1 and 3 standard deviations above the mean accounts for about 49%, 49 point some odd percent of all possible values. Conversely, below the mean, same story. But if I'm talking a Poisson distribution, that's a whole different critter. If I'm talking about something that's more concave or convex, that's really a different critter. And so it's understanding that. And once you see that, then you can filter down to the details of those arrivals or those service moments, or what we'd call product service moments, to be able to understand what's going on. Okay? Now, so we'll talk about that on Wednesday, and we'll talk about these functions. Now, I want to alert you to everything's going on, okay? And I want to take a look ahead as we move into near to the end of the semester. Module 12 is next week, and that's the 13th, 15th, and 17th, okay? And you can see what you'll have to do. And we'll move into the tree plan model. We'll look at it. And we'll look at, we'll do a little bit about, we'll look at forecasting, what that's all about, okay? And then you've got the PDC project chapter, and then an exam over chapter 13, 14, 15, okay? That's module 12 that's coming up next week. Then module 13, okay? And we have Thanksgiving holiday coming up, so we'll just have class that Monday. We'll talk about Pareto efficiency, the reciprocal lattice, and we're gonna look at the scoring model and the AHP models that'll be due on December 1st. Okay? Now, December 1st is a Friday, so I will not spoil your Thanksgiving. You're welcome. Now, Module 14. This is a time when now as you know, if you've had a class with me, I give you a major project or two and give you time to get ready to do the finals. Okay? And that's some time to work, it's flex time to work on these projects. Now let's look at what's ahead there. The SAP, okay? That business 1 part A, and the upload, SAP business part B, and the Anderson text, okay, is self-developed quiz over the Anderson text, and those are the instructions, and then up the upload. So you have those projects coming up that you'll need to be working on. Then we come down, okay, to finals, okay, and I'll click on my final exam schedule so you can see. Of course, this is all predicated when you meet, and we'll scroll down here and you'll see Management 3603 is the final exam period is 10:15 to 12:15 on Thursday the 14th of December. Okay? Now, if you've taken a course with me, you know that I'll have some things that are due, okay, prior to the start of the final exam period. So I'm going to have a final exam part A, which is due at the start of the final exam period, and part B that's due at the end. You say, can I work ahead and have it all done? Of course you can. I don't have any problem with that at all. Okay? So that kind of gets you where we are, what's going on. All right? Like I said, Wednesday we'll do some more we'll visit some more about these models, waiting line models, and the Poisson. We'll look at the normal inverse and the norm distribution models, and how we can take data and wash them up and clean them up and make them useful for us. And so that's pretty much it, folks, and I appreciate your time. And again, if you have any questions, shoot me an email. If I choose to if I choose to set up some virtual office hours tomorrow and Wednesday, I'll post something. What I'll do is I'll send everybody an email with a link if they choose to utilize them. I've had a few people, not too many, but some traffic. And, again, I'm always open to talking to you if you want to come in. If I'm not here, you can use the virtual office. You can ask questions, and the questions you ask they'll be masked, they'll be hidden, nobody sees them. Okay. Or if you say, could you on Tuesday at 7 o'clock. Could I have just a video conference with you, or could I have a video office? Yeah, within reason, I can do that too. Okay. All right, folks. Thank you so much. Have a good one, and I look forward to seeing your work throughout the week. Take care now.